Hello, everyone, and welcome to the second part of the first lecture in Tripoli 25. So, our topic is on probability models and actions. Previously, we had a short review of set theory, which includes defining what sets are and providing a set of notation and terminologies that is commonly used when we are talking about sets. And then we ended that leg of the lecture by presenting a list of operations uh, that is used on sets and how to visualize those operations using Venn diagrams. The next part of the lecture, uh, we will be talking about probability models, and specifically, we're going to focus on one of the components of a probability model, which is a sample space. So first, let's define what a probabilistic or probability model is. So basically, it's just a mathematical description of an uncertain situation, and it has two elements. So if we consider a stochastic experiment, which can be as simple as throwing a die or tossing a coin or getting a card from a deck. So, if you perform any of those experiments over and over again, you will have different results or outcome. And if we are talking about all the possible outcomes of that stochastic experiment, then we are referring to one of the components of the probabilistic model, which is the sample space. The second component of the probabilistic model uh, would be the probability law, and basically its job would be to assign probability values to each event inside the sample space. Now, to define the sample space, all you need to do is just list all the possible outcomes of an experiment, or if well, it depends actually. Now, if the sample space has a finite number of possible outcomes, then you can just list all the outcomes. But in the case wherein there is infinitely many possible outcomes of an experiment, then you can just use a rule, just like when we're describing sets. Now, since a sample space contains all possible outcomes, then we denote the sample space using the capital omega symbol, which is the same symbol that we use to refer to the universal set, if you can recall the previous part of the lecture. Now, a sample space has desirable characteristics, and usually these characteristics refer to the elements or the outcomes that is inside that sample space. And a desirable sample space should have elements that are, number one, mutually exclusive. And when I say mutually exclusive, uh, basically I'm saying that the all of the outcomes uh, of the sample space should be distinct from each other. Uh, I'm going to give you a non-example. So for example, our experiment would be the rolling of a six-sided die, and I chose my outcomes as follows. So it includes one possible outcome, which is 1 or 3, and another outcome, which is 1 or 4. So here, uh, this is not a desirable sample space because you have two outcomes that includes getting a 1, and these two outcomes so share that characteristics, so they are not mutually exclusive, and we don't want that. So we want the outcomes of an experiment or the elements of a sample space to be distinct from each other. Next, we also want the elements of a sample space to be collectively exhaustive. And when I say collectively exhaustive, I mean that all the possible outcomes of an experiment is included in that sample space. I'm going to give you another non-example, Let's say this time the experiment involves tossing a coin twice, and our job is to get the number of heads. So if I define my set of outcomes to be 1 and 2, then this sample space is not collectively exhaustive because I'm missing one possible outcome. Can you guess what that is? So here we have 1, so that accounts for the outcome we're in. You get one head, then a tail, or a tail first, then a head. The 2 here represents the outcome we're in. After tossing the same coin twice, you get heads in both tosses. What did I miss? 0. So this sample space does not include the 0. And that should represent the outcome of an experiment wherein after tossing the coin twice, you get tails on both instances. So this is not a collectively exhaustive sample space. So this is not a desirable sample space. So the next part of the lecture will just go through a couple of examples, and hopefully this will help you practice defining the sample space for a probability model. And here we consider a discrete or finite example, and we start with an experiment that involves two rolls of a four-sided or tetrahedral die. So instead of a six-sided die, imagine that it only has four faces. So if we say that the faces of the tetrahedral die involve the numbers 1, 2, 3, and 4, then we can visualize the possible outcomes of that experiment using this grid, wherein the x-axis would represent the first roll of the dice, and then the y-axis, this one right here, would represent the second roll of the die. And here I have labeled the I have used the faces of the die as labels to both axes. So in the event wherein uh, I rolled the die and I get 1 in both instances, then that possible outcome is just this ordered pair right here, 1 comma 1. Um, if I roll the die twice and I instead get a 2 on the first try and then a 3 on the second try, then that would be represented by this outcome right here. So the sample space would actually involve all ordered pairs that you can put in this cell matrix right here. And the elements of that ordered pair would be the x and y axis values, just like these two guys right here. And in total, you have 16 elements or 16 possible outcomes of that experiment. So is it a nice looking sample space? Do we satisfy the desirable characteristics of the sample space? So let's check. So is it mutually exclusive? So the answer is yes. So the outcome 1 1 is distinct from the outcome 2 3, and we can say the same thing for the other possible outcomes. Is it collectively exhaustive? Well, if we define all 16 outcomes right here, then we did not miss any outcome. So that is a good sample space. Alternatively, you can represent or visualize this experiment by using a sequential tree. So a sequential tree would look something like this. So you have here the root and the leaves would represent all possible outcomes of the experiment, and or basically the elements of the sample space right here. So you can distinguish one outcome from the other by looking at the path it takes from the root to the leaf. So for example, getting 1 on the first roll of the die and then a 3 on the second roll of the die would take you from the root down this path and down this path right here to get 1 comma 3, the ordered pair 1 comma 3. Alternatively, if we want to represent this outcome right here, the ordered pair 2 comma 3, so using a sequential tree, that would uh, require us to traverse this path right here. So this one, 2 for the first roll to die, and then for the second row, this 3 right here, leading us to this possible outcome. So that is the sample space for this particular example. So I also told you that sample spaces can have infinitely many possible outcomes, and one example satisfying that case would be this particular experiments. And let's say that experiment would involve throwing a dart to a square of unit area. And I'm referring specifically to this square right here. So one of the corners of the square is at the origin, and the length of the side is equivalent to 1. So the area is equivalent to 1. Now, if I add in an additional assumption that the dart would always hit the square, so what would be the sample space? Now, since the elements of the sample space is infinitely many, it would be futile to list the elements to describe the sample space. So instead of doing that, we're going to use a rule. And the sample space using a rule is defined as follows. So we have an ordered pair, x comma y, which represent the point at which the dart landed. And that ordered pair is defined such that x and y would have a value between 0 and 1, or exactly 0 or exactly 1. And that's it for the sample space of a probability or probabilistic model.